Good morning, everyone. In previous lecture, we have discussed about the singularity of complex valued function and also the different type of singularity. Today, I will start with the residue at different type of isolated singularity. You know that if a function is analytic inside and on a simple closed curve, then by Cauchy integral theorem, a line integral along that curve of that function is zero. Means if this function fz is analytic inside and on the boundary of this closed curve C. So when we are integrating this function fz along this curve C, it must be 0 by Cauchy integral theorem. But if integrand fz, if this integrand fz is not analytic at one or more points inside this inside this closed curve C, so it may be possible value of this integrand value of this integral is not zero along this curve. So it is maybe the possibility then we will not get the value 0 when we are integrating this function fz along that curve C. Okay, so now defining the residue of the function, analytic function, residue of and function at isolated singularities. For suppose that function fz is analytic everywhere, fz is analytic everywhere, yeah, at all point, at all point except z is equal to z naught. In that case, z is equal to z naught will be its isolated singular point. So we can expand this function about this z naught in Laurent series. So we can write this function, we can represent this function fz about this point in Laurent series, and Laurent series will be summation, its analytical part will be summation 1 to infinity an z minus z naught to power n plus summation, and going from 1 to infinity, this should be 0, sorry, it will be 0, from 1 to infinity b minus n upon z minus z naught to power n, or this can also be written as 0 to infinity an z minus z naught to power n plus b minus 1 z minus z naught plus b minus 2 z minus z naught square plus b minus 3 upon z minus z naught cube plus so on. It is the principal part, and this is the expansion of the function fz in some reason like z minus z naught less than r and greater than, but it is greater than 0. So in this annulus region, we can write this function fz as a in terms of as a Laurent series about this point z is equal to z naught. Okay, say that it is equation 1. Okay, so here this coefficient b minus 1, this coefficient b minus 1 of 1 upon z minus z naught in this Laurent series is defined as, it is called residue of the function, it is called the residue of the function function fz at this point z is equal to z naught. You know that bn is given by, you know that bn minus 1 is always given by 2 pi I integral along a closed curve C, and this curve C is lie totally inside the annulus. The C lie inside the annulus. Z minus Z naught R. So along this curve, Fz upon Z minus Z naught to power n plus 1 dz. Here this n will be 1, 2, 3 and so on. This n will be going from 1, 2, 3 and so on. Then b minus 1 will be substituting n is equal to 1 here. We will get, sorry, it should be minus n. It should be minus n. 2 pi I C Fz upon Z minus Z naught minus 1 plus 1 means Z naught minus 1 plus 1 dz is equal to 2 pi I integral along C of this function Fz dz. So b minus 1 is given by this formula. And this b minus 1, which is the coefficient of 1 upon Z minus Z naught in the Lorentz series, is called as residue of the function Fz at the point Z is equal to Z naught. It is generally denoted by, this is generally denoted by residue of the function at this Z naught. So this is the expression for evaluating residue at isolated singularity. Okay. So you know that for the removable singularity, you know that three types of isolated singularities are removable singularities, poles, and essential singularities. So residue at the removable singularity, is b minus 1, which will be equal to, you know that if Z is equal to Z naught is removable singularity for the function Fz, so the Lorentz series about this point Z is equal to Z naught, principal part of this series is containing no terms. There will be the no terms in principal part of removable singularity. And you know that b minus 1 is the first term, coefficient of first term of the principal part. So it must be 0. So for residue at the removable singularity must be equal to 0. Second is residue at pole. For suppose Z is equal to Z naught is the pole for the function, and this is the pole of order m. This is the pole of order m. So how we will evaluate this function? So in that case, b minus 1 will be m minus 1 factorial derivative of order m minus n. One second, we have to write here the limit. We will take limit Z minus Z naught m minus 1 of Z minus Z naught to power m of Fz. How we will evaluate this function? You know that Fz is summation an 0 to infinity Z minus Z naught to power n plus b minus 1 Z minus Z naught b minus 2 Z minus Z naught square, and it is the pole of order m. It means that principal part of the Lorentz series for this function will contain the term up to bm dash dash b minus m upon Z minus Z naught to power m. So this will contain this much term, and after that all the coefficient will be 0. So now multiplying this whole equation, say that it is equation 1, multiplying this whole equation by Z minus Z naught to power m. So multiplying this equation by z minus z naught to power m both side, it will give us summation n going from 0 to infinity a n z minus z naught to power n plus m, where this m is fixed. Okay, and b minus 1 will be z minus z naught to power m minus 1, b minus 2 into z minus z naught to power m minus 2, and last one will be b minus m. Okay, now differentiating this function both side, because this series, you know that if this if we are able to write this function as a Laurent series, so in the given annulus this series must be convergent, and in this annulus it must be convergent and also uniformly convergent. So in that case, if we are differentiating both sides, so we can differentiate this series term by term. So now differentiating both side of this function m minus 1 at time. So when we are differentiating it m minus 1 at time with respect to this z minus z naught to power m f z, m minus 1 a naught z minus z naught to power m plus a1 z minus z naught to power m plus 1, and so on, plus when you are differentiating this function m minus 1 at time, so we will get this b minus 1. When we are differentiating this function m minus 1 at time, it will give you m minus 2, m minus 3, and so on, z minus z naught to power 1. Okay, because we are differentiating it m minus 1 time. So this will be z minus z naught. In the same manner, this b m minus 1, ये वाले terms तो हमारे 0 हो जाएंगे, because it was constant, it will be 0 when we are differentiating it first time, and the next time b minus m minus 1, that term will be 0. So यहाँ पे कुछ terms हमारे क्या होंगे, 0 हो जाएंगे, and some term will be containing this type of term which is including the factor of z minus z naught. So now when we are taking the limit, both sides z is approaching to infinity. When we are taking m minus 1, m minus 1, m minus 1 एक सेकेंड, बी एम माइनस 1 होगा हमारे पास m minus 1, m minus 2 up to 3 to 1, and this will be m minus 2, m minus 3, and so on. Okay, z m minus 1, z minus z naught to power m f z equal to, you can see here when you are differentiating this function m minus 1 time, so limit z is approaching to infinity, z naught, and this will be a naught z minus z naught, and second term a1 will be z minus z naught square, and so on, plus b minus 1. In place of it we can write here minus 1 factorial, and second will be b minus 2. नेक्स्ट उसमें लिख देते हैं, when we are taking limit, when we are differentiating it m minus 1 time of this function, we will get factorial m minus 1 and a naught z minus z naught plus m plus 1, m, m minus 1, a1 z minus z naught square plus so on. Next, b minus 1 will be factorial m minus 1 plus b minus 2 will be m minus 2, m minus 3 and so on into z minus z naught. In the same manner, b minus 3 will be m minus 3, m minus 1 and so on. Okay, so when we are taking the limit both side, limit z is approaching to z naught, both side of this equation, fz. So you can see that when this term will be 0 when z is approaching to z naught, this term will be 0. So all the term will be 0 except this one because it is the constant. So we will get b minus 1 is m minus 1 factorial, and this will give us b minus 1 is equal to m minus 1 factorial limit z minus z naught m minus 1 derivative with respect to z, z minus z naught to power m fz. So this will be the expression for finding the residue of the function at the pole of order m. Okay. Next is residue at the isolated essential point. Residue of function at isolated essential point. You know that isolated, if z is equal to z naught is isolated essential part, in that case Lorentz series of this function fz about z is equal to z naught in its principal part has infinite number of terms. In that case residue will be b minus 1, which is the coefficient of, in that case we have to write Lorentz series of this function about this point z is equal to z naught, and b minus 1 is the coefficient of z minus z naught in Lorentz series expansion, in Lorentz series of this function fz above of this fz. Okay. Next topic is residue at z is equal to infinity. Residue at sorry z is equal to infinity. In the case if z is equal to infinity is isolated singularity for this function, where it is isolated singularity of function fz. Okay. If z is equal to infinity is isolated singularity for this function fz, so here we are consider a circle. Here we are considering a circle C, which is traversed in clockwise direction. This curve is traversed in clockwise direction, and this curve C is enclosing all the finite isolated singularity for this function. We are taking this curve C such that, say that this curve is mod z is equal to r. We are taking the radius of this curve such that it enclose all the finite isolated singularity of the function fz. So outside of this curve, outside of this circle means mod z is greater than, when mod z is greater than r, it means that outside of this circle the only singularity for this function will be z is equal to infinity. So in that case mod z greater than r will enclose only isolated singularity, only singularity of the function, which is z is equal to infinity. So it will be isolated singularity, and you know that residue at the isolated singularity is b minus 1, which will be, it will be 1 upon 2 pi I, because its value is 1 upon 2 pi I c, when c is traveling in anti-clockwise direction, इसको जब measure करते हैं, so fz dz. This will be the residue at z is equal to infinity. This is here residue of function of fz at z is equal to infinity. Okay, so this is the residue of the function at z is equal to infinity. Here I am taking a substitution, using a substitution. Let z is equal to 1 upon omega. Z is equal to 1 upon omega. So dz will be minus 1 upon omega square d omega. And accordingly, this curve will be also changed. So this will be 1 upon 2 pi I. 1 upon 2 pi I और डायरेक्शन यहाँ पे हमारी क्या होगी, रिवर्स हो जाएगी. So we will get here C. Say that now the curve is C star. This curve will be C star, and in place of z we will write here 1 upon omega, and dz will be replaced by minus omega square d omega. Minus omega square d omega. This will be 1 upon 2 pi I C star 1 upon omega square f of 1 omega into d omega. In place of this, we can write a new function, say that this is g omega because it is the function of omega. So minus 2 pi I C star g omega d omega, where g omega is 1 upon omega square f of 1 by omega. We are denoting by g omega 1 upon omega square g omega. Okay. So you know that when z is equal to infinity, then omega will approach to 0. So in that case, this is 1 upon 2 pi. You can see here 1 upon 2 pi I integral along this curve C star g omega d omega is representing isolated singularity of this function g about at the point omega is equal to 0. So this is the residue of this function g at omega is equal to 0. So we can say that residue of the function fz at z is equal to infinity is equal to minus time residue of this function g omega at omega is equal to 0, where g omega is omega is 0. So this is, it will be, because you know that residue क्या होता है इसका, it will be coefficient of 1 minus z naught. तो यहाँ पे हो जाएगा 1 upon omega minus 0 omega in Lorentz series of g omega. Lorentz series of g omega about 0. About 0. Okay. Now we will see some question based on the residue of the function. Suppose we have a function fz of this type z plus 1, z plus z minus 2. This is the function. Okay, you can see there it is a rational function, so it will be not analytic only at the point where denominator will be 0. So, and when the denominator will be 0, so all that will be the pole for this function. So here the poles of the function are, pole of this function fz are z is equal to minus 1 and z is equal to 2, and at this point numerator is not 0. So it is the simple pole for this function, and you know that for finding the residue of the function at this simple pole, z is equal to minus 1 will be 1 upon factorial m minus 1. So m is 1 here, so 1 minus 1 factorial 0. So its value will be 1. Limit Z is approaching to Z naught. Z naught is -1 here. So Z is approaching to -1. Derivative of order m minus 1. So m is 1 here because simple pole है तो order जो है वो 1 है. So m minus 1, it means that we will not take here the derivative of the function. Okay. Next will be z minus z naught to power m. Z naught is -1, so z plus 1 to power m. M is equal to 1 here into fz. Fz is z upon z plus 1, z minus 2. So z plus 1 will be cancelled. Z to power -1. So it will be -1, -1, -2, -3. So 1 by 3 will be the residue of the function at this point, -1. In the same manner, you can also find the residue of the function at z is equal to 2. In the same way, you can calculate this residue. Okay. Next, we have to evaluate the residue of the function at z is equal to 1 of the function 1 plus z square divided by z minus 1 whole square into z plus 2. Okay. So we have to find the residue of the function at z is equal to 1. You can see that z is equal to 1 is the pole for this function, but this is the pole of order 2 because at z is equal to 1, numerator is not 0. And you know that if z is equal to z naught is the pole of the function of order m, then we can define that function like phi z upon z minus z naught to power m, where this phi function will be non-zero at z is equal to z naught. So you can see that the remaining part of this function 1 plus z square upon z plus 2, it is non-zero when we are substituting z is equal to 1 here. So it means that z minus 1 square, it means that this is the pole of order 2. So z is equal to 1 is pole of order 2 for this function. So finding the residue of this function at z is equal to 1 will be 1 upon m minus 1. So 2 minus 1 will be factorial 1. Then limit z is approaching to this one, d by dz. M minus 1 means 2 minus 1. So d by dz into z minus z naught to power m. It means that z minus 1 to power 2 into function fz. So 1 plus z square divided by z minus 1 square, z plus 2, z minus 1 square will be cancelled. So here we will get z limit z is approaching to 1. Differentiating this function d by dz, 1 plus z square, z plus 2. So it will be, when we are differentiating this function, z plus z square, 1 plus 2z upon z plus 2 minus 1 plus z square, z plus 2 square. So now substituting this value of z here, so limit क्या हो जाएगी, 1 plus 2, 3 upon 3. So 3 by 3, 1 minus 3 upon 3 square. So this will be 1 minus 3 upon 1 plus 2 square, यानी 3 का square. 1 minus 1 by 3. This will be 2 by 3. So residue will be 2 by 3 here. Okay. और भी एक फॉर्मूला है for suppose if z is equal to z naught is simple pole of fz, and fz is of this type phi z upon psi z, and z is equal to z naught, this simple pole, or there is a no common factor between this phi z and psi z, then residue only for the simple pole. Residue of the function fz at z is equal to z naught is also write as phi z naught divided by derivative of this psi at this point z naught. So this is the also one of the formula for evaluating residue of the function if z is equal to z naught is its simple pole. Okay, now one more question related to the residue at z is equal to infinity of a function. So we have to obtain residue of function fz. This is z square at z is equal to infinity. So you know that whenever we have to find residue of the function at z is equal to infinity, we will use a substitution z is equal to 1 by omega. So correspondingly, GW will be 1 upon omega square into f of 1w. So f of 1 upon w will be GW is 1 omega square. F of 1w, fz is here z4 z square upon z cube. Okay, so f of 1 omega will be 1 upon omega 4 plus 1 upon omega square upon 1 omega cube. 1 omega square 1 plus omega square upon omega 4 1 upon omega cube. So 1 plus omega square upon omega cube. So you can also write it like 1 plus omega 1 upon omega cube. You can see here, this is the function g omega is the function of omega, and it is written in terms of omega, various power of omega. This is omega to power minus 1, this is omega to power minus 3. So this is we can say that it is the Laurent series of this function g omega about omega is equal to 0, and you know that in this series whatever be the residue of this function g omega at omega is equal to 0 is coefficient of, in the Laurent series of this function g omega about omega is equal to 0, coefficient of 1 upon omega. So you can see that here the coefficient of 1 upon omega is 1. So by the definition of residue of function at z is equal to infinity will be minus times residue of g omega at omega is equal to 0. So residue of this function at z is equal to infinity will be minus 1. Okay, so it is all about how we can calculate the residue of the function at various type of isolated singularity. Next topic is residue theorem. Residue theorem. So what is the statement for this residue theorem? For suppose that we have a curve C, which is simple, piecewise smooth and closed curve. And inside this curve and on this curve C, our function fz is analytic except at finite number of isolated singularities z1, z2, zn lying inside this C. It means that if we have a simple closed curve C, inside this curve C and also on the boundary of this closed curve C, function fz is analytic, but except finite number of points which are isolated singularity for this function, and all these points lying inside this C. All these points will lie inside this C. Say that it is Z1, Z2, Z3 and Zn. All these finite number of isolated singularities for this function exist, and all these singularities are lying inside this C. Then line integral of this function, line integral of the function fz along this closed curve C will be equal to 2 pi I summation of residue at all these singular points. So n going from 1 to n, यहाँ पे हम लिख लेते हैं r या I a जो भी लिखना चाहें. So summation r going from 1 to n, residue of the function fz at this point j is equal to jr. R we can say that 2 pi I will be residue of the function at z is equal to 1 plus residue of the function at z is equal to 2 plus so on. Last one will be residue of the function at zn. Say that it is denoted by r1. If it is denoted by r2, this is denoted by rn. So it will be 2 pi I r1 plus r2 up to plus rn. Yes, sum of residue of function fz at isolated singularity. So this is the residue theorem. Now we will prove this theorem. Okay, so you know that if this is the closed curve C, inside this and also on the boundary of this curve C, fz is analytic except all these points. Say that it is z1, z2, z3 and some more points, and this is zn. So now here we are considering a small circles. We can take a curve, a closed curve around this z1. Say that it is c1, and this curve c1 is enclosing only this singularity z1. It is not enclosing any other singularity. Each curve we will consider here a closed curve around each singular point like this. These curves will not include any other singularity. So this will be another curve C2. It is enclosing only this Z2, and in the same way Cn. So you can see that after excluding all these region which is enclosed by C1, C2, C3, C4 and so on Cn. So remaining part of this C, at the remaining part of this C, our function will be analytic. And this reason, if we are deleting this point, this part from this C, so our reason will be multiply connected reason. So it is the multiply connected reason. So by Cauchy integral theorem of multiply connected domain, we can say that line integral of this function fz along the outer curve C must be equal to sum of integral of this function fz along these inner curves. So by using Cauchy integral theorem, Cauchy integral theorem for multiply connected region, connected domain, we can write here line integral of this function fz along C must be equal to C1 fz dz plus C2 fz dz and so on Cn fz dz. And you know that if any curve is enclosing only one singularity, so then this singularity will be isolated singularity. And when we are evaluating integral of the function around this curve C1, which is including only single singularity of the function fz, so fz dz, this will give you residue of the function at z is equal to z1. So you know that residue of the function is 1 upon 2 pi I. Say that it is R1 2 pi I C1 fz dz. This is the residue for the function fz at z is equal to z1. So from here you can write the value of this integral. Integral c1 fz dz will be 2 pi I into r1. So in place of it we can write 2 pi I into r1. In the same manner, in place of this second integral we can write 2 pi I into r2. R2 is the residue of the function at this point z is equal to z2. In the same manner, this will be 2 pi I into rn. So 2 pi I plus R1, R2, R3 and up to Rn. So this is the complete proof of residue theorem. So with the help of this residue theorem, we can evaluate integral in the complex plane, या कह सकते हैं contour integration, and we can also find the integral of some definite real function. Integral of some definite integral of real valued function. We can also find that integral, improper integral or definite real integral with the help of this residue theorem. So first of all, we will see the example to find the integral in complex plane. So we have to use the residue theorem and find the integral exponential z minus 1 z minus 1 z minus I square dz. Here your fz is exponential z minus 1 z minus 1 z minus I square. Okay. So first of all, this curve C is given by mod z is equal to 1. You can see this function. This function has the pole at z is equal to 0, z is equal to 1 and z is equal to I. And z is equal to 0 and z is equal to 1 is simple pole and z is equal to I is the pole of order 2. So first of all, our reason is a unit circle around the origin of radius 1. This is the circle 1 minus 1 iota minus iota. So you can see that z is equal to 0 lie inside this curve. Z is equal to 1 is on the boundary of this curve and z is equal to I is also on the boundary of this curve. One second. रीजन हमारे पास ये नहीं है 1/2 है सॉरी 1/2 इट इज 1/2. So 1 will be here and this will be I/2 and here is also 1/2 minus 1/2. This is minus I/2. I is something here. Okay. So you can see that in that case only z is equal to 0 is the pole which is lying inside this closed curve C. So z is equal to 0 is only singularity, only singular point, simple pole lie inside this curve C, inside this curve C. So in that case, line integral of this function around this C must be 2 pi I residue of the function at z is equal to 0 क्योंकि इस कर्व के अंदर केवल एक ही पॉइंट है जहां पे फंक्शन हमारा सिमिलर है. So residue of this function at z is equal to 0. This will be the answer. You can find the value of this residue function. तो ये वैल्यू आप आसानी से फाइंड कर सकते हैं. तो हम ये इसे इवेलुएट नहीं कर रहे. आई एम लीविंग दिस ऑन यू. You have to evaluate this function at z is equal to 0. Second thing is we are taking a function. We are taking a curve which is mod z is equal to 2. In that case, all these three singularities will lie inside this curve. ये मान लीजिए z is equal to 2 है. So 0 is lying here, I is lying here, and 1 is lying here. In that case, line integral of this function fz dz must be equal to 2 pi I r1, r2 and r3, where r1 is residue of the function fz at z is equal to 0 and r2 is residue of the function at z is equal to 1 and r3 is residue of the function at z is equal to I. सारे रेसिड्यू निकाल सकते हैं and then we will substitute the value of r1, r2, r3 here. We will get the solution. Okay. So what will be the r1 here? Fz was exponential z minus 1 z minus I square. Fz is exponential z minus 1 z minus 1 z plus z minus I square. I think so. Yeah. So limit z is approaching to z naught. Z will be cancelled. Z minus 1 z minus I square. Zero. 1 minus 1 0. Next r2 will be the limit z is approaching to 1 exponential z minus 1 z minus I square. E minus 1 1 1 minus I square. R3 will be limit z approach to I d by dz exponential z minus 1 z minus 1. So you can evaluate R3 from here. Next topic is with the help of residue theorem, we have to evaluate real definite integral, evaluation of real integral using residue theorem. So first integral in this category is real definite integral involving trigonometrical function trigonometric functions. For suppose we have an integral like integrate from 0 to 2 pi of this function f of sine theta, cos theta, d theta. Okay. So f is a real valued function of this sine theta and cos theta. Here we are using a substitution ei theta, which can be write as cos theta plus I sine theta. So from here dz will be ei theta into I d theta. So d theta can also be write as dz upon I ei theta, or we can say that d theta upon dz I into z. And you know that this cos theta can also be write as ei theta plus minus I theta upon 2, which can also be write as z plus z inverse upon 2, and sine theta is ei theta minus e to power minus theta upon 2i. So sine theta can also be write as z minus z inverse upon 2i. So we will use all this substitution here. So correspondingly we will get the integral fz, where this fz is f of cos theta. Cos theta is z plus z minus 1 by 2, and sin theta is z minus z inverse upon 2i. So this is f theta, and in place of d theta we can write dz upon iz. And you know that because we are taking z is equal to ei theta. So when theta moving varies from 0 to 2 pi, so it will make a circle of radius 1. This will produce a circle of radius 1 about origin when theta vary from 0 to 2 pi in anti-clockwise direction. So we can replace this integral by a contour integration where c is the circle defining by this. So जो line हमारा real integral था, which is involving sin theta and cos theta, we can replace that integral by this value. Okay. So finally we are getting this type of function, and you know that अभी हमने इस तरह के function को, अगर इस तरह का function है, so we can find the integral of this function along this closed curve C with the help of residue theorem. यहाँ पे हमारे पास क्या हो जाएगी, residue theorem के according fz upon, या ऐसे ही लिख लें, iz dz. This can also be write as c. In place of this we can write here gz dz. So this will be 2 pi I sum of residue, sum of residue at isolated singularity of gz of function gz. इस पर बेस क्वेश्चन हम ट्यूटोरियल क्लास में बता देंगे या नेक्स्ट क्लास में we will discuss about how we can solve this type of questions. Okay.